Hi, my name is Liam, and today I'll be presenting our work towards beginner-friendly LLMs for language learning, controlling difficulty in conversation. This is joint work with my collaborators, Emma Jin and Chris Callison-Birch at the University of Pennsylvania. Okay, let's get started. So when learning a language, there are generally 4 core skills that you need to acquire. That is reading, writing, listening, and speaking. Of these 4 skills, 3 are significantly easier to acquire on your own time. For reading, you can simply download books or news articles in the target language and then read. For writing, you can just get a notepad and practice writing sentences. For listening, you can listen to podcasts or TV shows in the target language. But the final one, speaking, is pretty much impossible to practice on your own. In order to effectively practice speaking, you need access to either a native speaker for conversation practice, or you need to sign up for classes. This can be prohibitively expensive for a lot of people, or just downright impossible depending on the region of the world that you're from and, let's say, the rarity of the language that you're trying to learn. And so this motivates our desire to want to practice speaking with large language models. But there's a problem with practicing, which is that language models output at a near native level, and so therefore they're not really suitable for language learners who naturally are below native level and potentially even at a beginner level. And so this motivates our paper, which is to test different methods for trying to control the proficiency level at which a language model speaks so as to better suit beginner language learners practicing their conversational skills. Okay, so let's start by defining the task. The task of conversational difficulty control we define as facilitating casual conversation between a particular student at a specific difficulty level, and then a difficulty-controlled language model. Our main criteria are understandability, that is, how much of the language model's output is the student capable of understanding, and fluency, which is, was the output fluent and natural sounding text. For our particular study, we target the Japanese language. This is primarily because myself and my co-author Emma both have experience learning Japanese as a second language through classroom settings, but also because Japanese has become particularly popular as a second language to learn in many American universities, and therefore we had a very large population of students to draw from when doing user studies. For our different difficulty control methods, we started with 2 baseline methods. That is, a baseline prompt, which prompts the model just to output in the target difficulty, but doesn't describe the difficulty further than basic terms such as beginner or intermediate. The second prompt was a much more detailed prompt that listed off the known vocabulary of the particular student, gave example conversations at the student's difficulty level, and then gave a more detailed description of what their level entails and what sorts of things they're comfortable speaking about. The next 2 comparisons we did was an overgenerate and rerank comparison, where we generate multiple candidates from the model and then output the candidate that minimizes the estimated percentage of tokens above the student's target level, and this percentage of tokens is estimated using various corpus level heuristics. And finally, we have the fudge method, which biases the model's next token logits using a lightweight difficulty classifier. And so it's worth talking a little bit in more detail about this fudge method. So like I mentioned, we train a lightweight classifier to predict the future difficulty of a text given a prefix, and then we interpolate those predictors logits with the model logits. So at the bottom, you'll see the equation. It's very basic stuff, but the reason why I bring this up here is because of this parameter lambda. So as we increase the value of lambda, for example, from 0.6 to 0.7 to 0.8, we are increasing the amount of influence the predictor model has on the output logits and decreasing the influence of the core language model. So difficulty control goes up at the expense of fluency. Okay, so now how do we evaluate these methods? So in our paper, we have 2 different evaluation settings. We have an automatic eval and a human eval. We'll start by talking about the automatic eval. For our automatic eval, we have a self-chat pipeline. Put simply, this is just simulating a student with an LLM and then having these LLMs chat with each other and then evaluating whether or not the tutor is able to actually output at the target difficulty level. For the student model, we just fix it constant for every single comparison that we do. We have it be the Quen 2.5b, 2.572b instruct model, and we give it a fixed prompt that just says output as if you are a student and you're trying to talk with some tutor. For each of our tutor models, we simulate 75 dialogues with a student model at 5 different levels, from beginner all the way to expert. If you want more details about the self-chat pipeline, please consult the paper, but I'll just get into the sort of results. In the first 3 columns, we have our fluency metrics, that is to say average length in tokens per utterance, average perplexity, and then trigram diversity. And for the final 3 columns, we have the difficulty control metrics, that is J-readability, token miss rate, and control error. Our first finding is that fudge performs the best across all of the different methods at controlling output difficulty at the highest values of lambda. It's also worth noting that even at lower values of lambda, if you hold the same model constant, that is compare quen to quen, fudge also does the best across all of the different methods at lambda of even 0.25. Our second finding is that increasing the value of lambda doesn't substantially reduce the fluency of outputs as much as one would expect. We did notice that once you get past 0.9, then the fluency starts to really degrade much more quickly, but up to 0.9, fudge still outputs very natural sounding dialogue. Okay, so automatic eval results are great, but we need to actually test this on real beginner Japanese speakers. And so we conducted a user study with first and second year students from Japanese language courses at Penn. In order to recruit these students, we sent out recruiting materials such as flyers via email. We contacted instructors and posted on Canvas platforms for the students. And we were able to recruit a population of student learners that was primarily in the beginner level. As you can see from the hours spoken per week, on average, our students are speaking 1 or fewer hours of Japanese per week, which is surprising given that they're active students in Japanese classes, but I digress. Point is that this is a population of speakers that don't get conversation practice otherwise. And it's also important to note that this is the first study of its kind. All of the previous work always used conversationally fluent or business fluent speakers when testing AI conversation partners, and we're the first to target these beginner learners specifically. In order to facilitate our study, we also built this interface. The bottom of the interface has this microphone icon, and this is so as to give the students control over when they decide to speak. For each conversation turn, students are given time to think over their responses, and then they hold the microphone button down when they want to speak. When they release the microphone button, their speech is then transcribed into text, sent to the model, and the model responds using, and then the model speaks its response using the OpenAI TTS. All of our comparisons were done on Quen 72B and queried via a local server. Furthermore, all of our comparisons were done in a double-blind fashion. So all of the model names were abstracted to A, B, C, D, so that neither the participant nor the proctor knew which model was coming up, and the order of the models were randomized each time. For each session of 45 minutes, the student conducted a full conversation with each of our models, so every student got to see every single model comparison. After each conversation turn, the students manually highlighted which specific words in the response they did not know and gave an overall judgment as to whether or not they understood the tutor's response. And finally, after each full conversation was done, we gave the students the following survey and asked them the following questions on a 1 to 10 scale. How much could you understand of the bot's speech? How effortful was it to talk to the bot? How comfortable did you feel? And then did you feel like the bot's responses were natural? Note that 2 of these questions are difficulty related and 2 of them are fluency related. Okay, and these are the final results for the human evaluation. The main finding is that fudge does even better on this setting than it did in the automatic evaluation. It's also second best in the fluency category, second only to the overgenerate method. Another point to note is that the total percentage of rounds manually annotated as understandable by the students improved quite substantially from the baseline case to the fudge case. In the baseline case, fewer than half of the rounds were understandable, whereas in the fudge case, over 80% were. Now, of course, 80% isn't 100%, and we think there's a lot of room for future work to improve on our results, but we still think that over 80% starts to get into the realm of feasibility. Another more important thing to look at is when you break this out over time, we notice that the prompt-based methods gradually weaken over multiple rounds of conversation. That is to say, towards the end of the conversation, the prompt-based methods were much worse at controlling difficulty, whereas fudge stayed relatively consistent over time. So to recap, we propose and motivate the task of conversational difficulty control, and we conduct the first ever study of beginner students working with AI chatbots. We show that prompt-based methods generally weaken over the course of a conversation and are thus not quite suitable at the current moment for difficulty control. And as an alternative, we show that modular difficulty control methods such as fudge can improve comprehensibility for beginner learners over the course of the entire conversation and are promising first steps towards actually solving this problem and making language learning more accessible to all students. So thank you so much for listening to this talk all the way through. If you're interested, please check out our paper. The QR code is on screen now. So thank you so much.